Lecture 5.8, Capacitor Reduction Techniques. So what we want to do here is apply series and parallel characteristics to capacitors. And one of our main things that we're going to use here is the capacitor equation. So what we want to do is set up a table, a summary table of how capacitors behave in series and parallel. So this is going to be a summary table of series and parallel characteristics. Of capacitors. So just a couple of things here. We have to use the capacitor equation. So in other words, the charge has to be equal to the capacitance times the voltage. We talked about current. When we think about current, it's proportional to charge. And our understanding here for the parallel plate capacitor is it depends on A over D. So everything that I'm writing is going to be in this set right here. So let's set up a table. So the thing that I'm going to have to worry about is sort of like scaling this table. So I will adjust the lengths and everything. So the first thing that we want to look at is probably, I'm going to say that I'm going to make a column on capacitance. And then I want to make a column just on voltages. And then finally, I want to make a column on charges. So I'm going to guess that it's going to take me all the way to about right here. So I will adjust everything. So now let's start talking about series. So if I say the word series, what this means here is that we increase distance. Okay, we're going to increase distance. So here's what I know. If I have capacitors in series, then 1 over series is equal to 1 over C1, 1 over C2, 1 over C3. Their inverses add where C series is always smaller than the smallest capacitor in the circuit. That's what we mean by series. And then voltages, when they're in series here, we then say that voltages are divided. And so what we're going to see here is that the voltage of a branch is then going to be a combination of the sum of the voltages, depending on how many they are. So in series, we only have one loop, so therefore the current is the same. So if we have series capacitors, then their charges have to be the same. So the charges are the same. Now, when I'm looking at this thing, what you want to pay attention to is that we want to continue to keep thinking in that image that we had with the circuits here. So if I can calculate the series charge, then it's going to be equal to any of the charges for the capacitors that are in parallel. So now that's how I'm summarizing series. Now we're going to go to parallel. So if I have parallel capacitors, it increases area. So then we go that C parallel, because area is directly proportional to capacitance, then however many capacitors I have in parallel, they add directly, where it's the opposite here. C parallel is always greater than any capacitor value. For parallel, there's only two equipotentials, so therefore we say that voltages are the same. They are not divided. So in this case, we'll have the voltage of a branch will then be equal to all of the possible parallel branches. And then finally, we then say that since current is divided in parallel, we then say charges are divided in parallel, such that the total charge, the parallel charge, is a combination of all of the individual capacitors. That is the charge on them. So before we start looking at examples, I'm going to use this table heavily. Okay, so this is super important to understand. Before we get started, I want to show you a little bit of an algebra trick. Okay, so this is what I'm going to call, so there's a shortcut when dealing with two capacitors in series. And what I'm going to do is, because there is no name, it's just an algebra, it's not anything tricky. What I'm going to do is that I'm going to call this Carlos's trick. It's not mine. I'm sure somebody showed it to me. I just don't remember who did it. Now, the reason it works is because textbooks typically use nice values. So this trick usually works very well because textbooks, or just problems in general, use nice valued capacitances in problems. That's the only reason why we can do that. So then let's look at this. So if I have two capacitors in series, then that means here is that I have a capacitor here and a capacitor here. And you can see here that when I look at these, I have charge capacitance 1 and capacitance 2. And you can clearly see that these guys in series, because there's only one connection between these two. That means here is that I can replace this with a single capacitor called the equivalent series. capacitance. So what does this look mathematically? So if I look at the table, if I have two capacitors in series, it's their inverses that add. So mathematically, we write that 1 over C series is equal to 1 over C1 plus 1 over C2. It turns out that that's not a very good way to write it. So if you do the algebra, this is what you're going to find. It turns out that this is C1 plus C2 times the combination C1 times C2. So if I invert this, I get a very nice relationship that comes in very handy. It says C series, we don't deal with the inverse, is a combination of C1 plus C2 times the product of both of them. I strongly suggest that you memorize this. Okay? And this is what I call Carlos's trick, just because I didn't have a better way of saying that. So let's go look at this and apply examples to this. Okay. So the first thing that I'm only focusing on is capacitance. So here's example 1. So when I'm looking at this example, here's what I'd like to do. I want to reduce a combination of capacitors into a single equivalent capacitance. So the goal here is to reduce this combination of capacitance into a single equivalent capacitance. So let's draw it out. So here's my circuit. I'm going to start here. I'm going to come in and I'm going to have a capacitor here. Then it's going to split. Then it comes back together and I have another capacitor right here like this. So when I'm looking at this, I'm going to call this A and I'm going to call this B. And then these capacitors has a series of values. So they're in units of microfarads. And our whole goal is to replace this with a single capacitor. And this single capacitor is what we call the equivalent capacitor, AB, because each of these nodes are labeled AB. So when I look at this thing, one of the things that we want to pay attention is that we want to go through a process. Okay? We want to go through a process. And so the process goes something like this. We ask ourselves, how do we reduce this combination using series and parallel techniques? The first thing you got to do here is that you have to use colors. So I'm going to copy this because I'm going to need this. And what you're going to see here is that I'm going to keep modifying this thing. So rule number 1, which I think is important for a new student. Use colors to identify nodes, which is the same as equipotentials. So we're just looking for wires. So then once I do that, then I'm going to start to ask the next question. What is in parallel? If it's in parallel, then that means that there are two colors connecting two capacitors. So if that's the case here, then we know that C parallel is just then the combination of C1, 2. And then we're going to ask, what is in series? And if that's the case, we then have one color connecting two capacitors. So then we come in and then we replace it with this series combination. But God knows, please don't do that. We want to use C series as C1, C1 times C2 divided by the sum of those. So here we go. So the first thing that I'll do is that here's my circuit, and I'm going to ask what's in parallel. Okay, so the first thing that I do here is that I got to draw my colors. So let's start drawing colors. So what I'm going to see here is that right here, I'm going to call that purple. And then the next one here, I'm going to call this orange, and I'm just coloring my wires until I get to the next one. And then here you could see is that I have a single wire here. And then finally, I get this guy right here. So you could see that I've color coded this. So now I'm asking the question, what's in parallel? So I'm looking for two colors here. So if I look at that, the first thing that jumps out to me here is the orange and the blue. So that tells me that I have the orange slash blue have two caps in parallel. So now I'm going to reduce them. So then that tells me here is that if I look at the combination of the orange slash blue, then these guys are in series, which then should be 8 plus 5, excuse me, I said series, I meant parallel, then that should give me 13 microfarad. So now what I do is that I take this circuit here, I take this combination of capacitors, and now look what I'm going to do. I'm going to take this guy, and now I reduce my circuit. I'm going to come in here, and I'm going to then replace that 8-5 combination with one capacitor. So if I look at this thing, so then if I take this guy, and I just place it here, now what I've done here is that I'm going to erase all of this because it doesn't exist anymore. So what do I have? I now have a new capacitor like this, and you can see here is that now that value of this capacitor now, which we just calculated, was 13 microfarads. This is the combination of 8 plus 5. So this is now 13 microfarads. So this now is my new circuit here. So I can see here is that all of these capacitors only have one color connecting them. Therefore, they must be in series. So now if I look at this, then I'm going to ask, what is in series? Well, if I look at the circuit here, I now have this, and I'm now going to get rid of the 5 and the 8, and I'm just going to look at this guy here. Now, there's multiple ways to do this. Okay, multiple ways to do this. So what I'm seeing here is that mathematically, textbooks try to tell you that I can read, since all of these are in series, I can rewrite this as A, and then I could make the combination of C1, C2, C3. And by the way, it's because I'm adding numbers, I can also manipulate these guys so that I could have C1 plus C3 plus C2. I can manipulate these any way I want. So let me adjust this thing here a little bit, and then let me show you what this means. So I can move capacitors around. I don't have to keep them in this combination. Maybe what might be better for us is that what might be easier to manipulate, where now we change the location of the 8 and the 13. I can do that without a problem. So any way that I can manipulate these to actually do this is better. Now, if I look at this mathematically, this is the algebra equation that I would have to solve. So if I look at this thing, then I would say that textbooks tell you to do this. They then say that 1 over CAB is then going to be 1 over 10, 1 over 8, plus 1 over 13. And of course, these units are going to be in 1 over microfarads. So a lot of the times, this can become quite cumbersome. And the reason why is that it's a nightmare to actually do that. So most of the time, you should be sticking that into your calculator. So what am I going to do here? I am going to apply Carlos's trick to reduce this quickly using 2 steps. So I'm going to say that this is the circuit. I could have dealt with that one, but I'm going to say I'm going to stick with this one since I just redrew it. So now let's do this. So the 2 steps that I'm going to look at here is that I'm going to say the first thing is that I'm going to focus on capacitors 1 and 2. So what's 1, 2, and 3? So for the sake of simplicity, I'm just going to just go down and go like this is 1, this is 2, this is 3. So what I'm doing here is that I'm going to focus on these guys. So now I want to reduce C1, C2 into a capacitance that's equal to C12. So how do I do that? The way I do this is I go the following way. So this says that C12 should be 1 over C1 plus 1 over C2, but then I use my trick. And if I use my trick, it's then C12, and then it's going to be the combination of these two, which will then be 10 times 8 divided by 10 plus 8. And if I look at my numbers, this is 80 divided by 18, which is then going to be 40/9 microfarads. So that tells me that I have a capacitance for those two guys that reads like this. So now, what does my circuit look like? Well, I reduced that combination, right? So now we can rewrite the circuit as follows. I could then come in here and go, I'm going to paste this guy here. And we just calculated that as 40/9. By the way, 40/9, what is that? 36.4? Something like that. But all I'm saying here is that now this is a capacitor of 40/9 microfarads. So then that means here that the equivalent circuit then, look what happens now. So if I paste this guy in, what happens here is that now I have removed the orange. I only have one capacitor now. And this capacitor I'm going to call 1, 2, and this is 40/9 microfarads. And that's my circuit right there. So when I'm looking at this guy, what you're seeing is that now I am left with two capacitors in series. So now what am I going to do? I'm going to apply Carlos's trick again. So if I do that, now look at that. I have two capacitors between A and B. Now note, I could write 1 over CAB, and then I'll go 1 over C12 plus 1 over C3. But why do that? Why can't I just immediately come in here and go CAB is then going to be the combination of C12, C3 times the combination of the two multiplied. So if I now multiply these guys out, I then get that this will be 40/9 times 13 divided by 40/9 plus 13. And if I calculate this to 3 sig figs, I'm going to get, or 2 sig figs, I get 3.3 microfarads. And that is the equivalent capacitance right there. So now if I look at my whole circuit, here's what I find. One can replace the combination of, and I have to go all the way back up, right? This is my circuit right here. So if I copy this, I can replace this combination right here with a single capacitor. A single capacitor that now, if this is A and this is B, this is the equivalent capacitance, CAB, which is equal to 3.3 microfarads. That's what we just did. So this is what we wanted to show. So let's go to the next example, and we're going to do the exact same thing. So in this example, I want to do a different style. That one was more series. This one is going to be more parallel. And it goes like this. So we want to calculate. So I don't know what I said before. What did I write before? I probably said something, I don't know. Let's say that we're going to reduce some combination. We're going to reduce some, we're going to reduce this combination into a single equivalent capacitance. So now all we have to do is go in and look at what that is. So I did A and B, so let's change this a little bit. So I'm going to say that this guy, I'm going to call X. And now what I'm going to do here is that I'm going to draw 3 capacitors in series. And I think I like the idea of making this a little bit longer. And then I'm going to have 2 capacitors that come out like this. So now I'm just going to give these values, and I'm going to say that this is 18. In this case, it's going to be nanofarads. This is 7.5 nanofarads. This is 30 nanofarads. This is 10. And then finally, this is 6.5 nanofarads. So now my whole goal is to replace this with a single capacitor with capacitance CXY. So now we start the same process. The first thing I want to do is that I want to put in colors. So let's do that. So my first color is going to be this purple. I'm filling purple. And then I'm going to have an orange here. Then I'm going to go to blue. And then I'm going to go to green. So each of these are my nodes here, my equipotentials. So now that I look at this thing, the first thing that we want to do here is that we want to add all of these and identify what's in parallel and what's in series. To me here, the most pressing one is the guy here in the middle. You could see here that the 1830 and the 10 right smack in the middle, they have one color between 2 capacitors. So what I'm going to say here is that I'm going to say what is in series. And what I'm seeing here, the 3 caps in the middle are all in series, since one color connects each capacitor. So my goal here is to reduce this. So then when I'm looking at this, I want to take those and start to add them. So if I look at this thing, here's what I'm seeing. I have this guy all in series here. And what you're seeing here is that this is an 18 nanofarad. This is a 30 nanofarad. And then this guy is a 10 nanofarad. So now when I'm looking at these combinations, my whole goal here, I don't know what the colors are. This is orange. This is blue. And then this one is then going to be green. So I want to get that combination right there. So the question is, which combination do I want to do? And it seems to me that the easiest combination would be the 30 and the 10. So let's go look at that. So if I'm looking at this thing, I'm going to pick two of the capacitors. So I'm going to focus on these guys. So I could come in here and I could call this, how about 1, 2, 3. So I'm going to focus on these two. It does not matter which order. And I'm going to call that capacitance 2, 3. So I see that these guys are in series, which then tells me that C23 is then going to be C2, C3, the combination of C2 plus C3. And so if I look at this, then this is going to be 30 plus 10 times 30 times 10. So you could see here that's 300 divided by 40. You're going to get 15 divided by 2, which is then 7.5 nanofarads. So after my reduction here, I can now replace this guy, right? I could now come in here and say that after reduction, I have this combination. And I can replace this guy because I just calculated this guy, and this guy is 7.5 nanofarads. In other words, I have a circuit that now reads like this. I have this capacitor, and I have this capacitor, and I could see here that I have my purple here, I have my green here, so the only color that's left is the orange. The blue is gone. So if I start to look at these capacitors, the bottom capacitor is now going to be 7.5 nanofarads. The top capacitor is going to be 18. So this is 1, and this is the 2, 3 combination. So then I repeat the same process. Okay, so if I repeat the same process, what that tells me here is that now I can now do this combination. So if I look at the capacitance of 1, 2, 3, this is then going to be the capacitance of 1 times the capacitance of 2, 3, 1 plus 2, 3. And if I plug in my numbers, this is then going to be 18 times 7.5 divided by 18 plus 7.5. And when I compute that number, I get 5.3 nanofarads. And this is the combination of 1, 2, 3. So now I have reduced those three into that circuit right there. So now, what does my picture look like? This is my picture here, and I want to take this with me. And I'm going to say that now I'm going to redraw my picture. And this is what I get. I find that I have this guy right here. This is what we started with. And what I can do now is that I can replace this with this capacitive circuit here. I'm going to have this guy's going to be 6.5 nanofarads. I'm going to have my capacitance that I just calculated. What was that value that we calculated? 5.3 nanofarads. So this is then going to be 5.3 nanofarads. And then I'm going to have my third here, which will then be 7.5 nanofarads. So when I'm looking at my circuit, this is the combination that I have. This is X, this is Y. I still have my purple node right here. I still have my green right here. But the blue and the orange are now gone because of reductions here. These are all in parallel. Because they're all in parallel, I could then go in and just add them. These are all in parallel because there are two colors only. That's the definition of parallel. So this tells me then that now the capacitance CXY then has to be a combination of 6.5 plus 5.3 plus 7.5 nanofarads, and this quantity is then going to be 19 nanofarads for CXY. So now I know the full capacitance. So in other words, we have this. The bottom line is that we started with this circuit and we have now replaced it with a single capacitor, single equivalent capacitor, where this is Y, this is X. Again, this is my purple, this is my green here, and this just says that CXY is then equal to 19 microfarads.